Hello everyone, welcome to the lecture Digital Logic Design. I'm Dr. Vilayat Khan. In today's lecture, the major topic is combination logic with MSI and LSI. The subtopics are decimal adder and BCD adder. In this lecture, I will teach you how to design a decimal adder, and in particular, I will take an example of designing a BCD adder. So, what is decimal adder? In computers and in calculators, a decimal adder adds two decimal numbers, and for any binary circuit to add or logic circuit to add two decimal numbers, the numbers must be in a binary code. For example, there are a number of binary codes to represent decimal numbers. The most popular is BCD code, which is binary coded decimal. There are other codes to represent decimal digits, for example, XS3 code and many others. In this lecture, I will take and consider BCD code to represent decimal numbers and then to add decimal numbers. So the adder that we would be designing is to add decimal numbers when they are encoded using BCD code. So such kind of adder would be called BCD adder because the numbers are encoded in BCD code. So what is a BCD adder then? The diagram shows a BCD adder actually adds two BCD digits. Here there is a one BCD digit encoded as a 4-bit code, binary coded decimal, and there is another BCD digit which is also encoded in 4 bits code. So this would get a BCD digit 0 to 9, and UD digit is encoded in BCD code, a 4-bit code. And similarly, the other digit is also encoded in BCD, a 4-bit code. And there is an initial carry, which is carry in. And this BCD adder would take this input carry, the 4-bit first number, the 4-bit second number, and this becomes 9-bit, and it would result a 4-bit sum and an output carry. So our final BCD adder should look like this. To design a BCD adder, the classical method or the K-map method would require to begin with a truth table, and in that truth table, as we have seen a number of examples in the previous lectures, in the truth table there must be columns for the inputs. As we can see in the BCD adder, there are 9 inputs, so we would require 9 variables, and we would need a 9 variable K-map to simplify the Boolean functions, and the truth table would require 2 raised to power 9 entries, which becomes 512 entries. So this is quite huge truth table, and it would be quite difficult to write such a table on the paper, and then obviously it is even more difficult to simplify 9 variable Boolean equations. So another method is to use combinational logic with MSI and LSI, but this requires clever thinking. Each time when a combination logic is used to design a circuit, then one must be looking for new algorithms to design a circuit. So we would be adopting this approach to use combination logic with MSI and LSI to design a BCD adder, and I will show you that this kind of thinking is sometimes much better than the classical method. Okay, so to design a BCD adder, we must first understand the binary adder, how it would work, the binary adder, the functionality of the binary adder. So a binary adder, actually, we have already designed such a binary adder in previous lectures. So a binary adder would take a 4-bit binary number, and if we are talking about 4-bit binary number, then it would take a 4-bit binary number here. This is the first number, and this is the second number, which is also a 4-bit binary number. And initially this would get an input carry. So this 4-bit binary number would take this input carry and the 4 bits of the two numbers, and would result 4-bit sum and an output carry. These letters are different in different diagrams, but the concept is the same. So for example, in the previous diagrams we have used S1, S2, S3 and S4, and in this diagram we see that Z1 and Z2, Z4 and Z8 are used. So it is just a matter of test. Variable, any variable can be used. Okay, so this binary adder takes two 4-bit binary numbers, an input carry, and a result a 4-bit sum and an output carry. So this is how a binary adder look like. Now I will be using a binary adder to implement a BCD adder, and we are not going to use the classical map method, and instead I will use the combination logic using MSI and LSI. So as a MSI chip, this 4-bit binary adder would be used, but remember that a 4-bit binary adder and BCD adder are different from each other. The outputs of a 4-bit binary adder is sometimes the same as the BCD adder, but it is not always the case. So we have to identify those cases when the output of a 4-bit binary adder is different than it should be in case of a BCD adder. So in the coming slides I'll investigate where and when the output a 4-bit binary adder is different, and how to make it equivalent to the BCD adder output. Okay, so each time in the BCD adder, each time when a BCD digit is two BCD digits are given as an input to the BCD adder, a BCD digit, we know that 0 to 9 are the BCD digits. So a BCD digit can be 0 to 9, and the other BCD digit to the BCD adder can also be 0 to 9. So it means that when the BCD adder is used at maximum, when one of the digit is 9 and the other digit is 9, then the sum can be 18. And if the input carry this particular input combination is also 1, I mean the input carry is also maximum, then the total sum becomes 19. So 9 is the first input digit, and the other input digit is also 9, and we assume that the input carry is also 1, the maximum. So the maximum sum can be 19. The sum can also be 0, it can be 1, it can be 2, but the maximum can be 19. So let's assume that the sum of the adder is 0 in decimal, and in the binary sum would be in binary. If, for example, if we are using the binary adder, 4-bit binary adder, then it would be, the sum would be 0, 0, 0, and the output carry would be 0. We are using Z1, Z2, Z4 and Z8 for the binary sum bits, and for the output carry we are using K. These subscript with the Z just represent the weights of the bit or the position of the bit. Okay, so if the sum of the adder is 0, then in binary the 4-bit sum bit would be 0, 0, 0, 0, and output carry would be 0. And if the sum the output sum is 1 and decimal 1, then the binary sum would be 0, 0, 0, 1, and the output carry would be 0. And similarly for 2, if the output sum is 2, then the binary in binary this 2 would be 1, 0, as we already know. It's very simple, and output carry would be 0. And similarly for 3, the output would be, the binary sum would be 1, 1, and the output carry would be 0. And if we continue this until 19, we would get this table. So for the 19, it is the binary equivalent of 19 is this. So this also indicates that when the number increases from 15, then for 16, 17, 18 and 19, as these 4 numbers cannot be accommodated in 4 bits, this increases till the 5 bit, and we get the output carry as 1. So these are the binary representation of these decimal numbers. So whenever 2 digits are given as input to the binary adder, we are assuming that we have a binary 4-bit binary number, 4-bit binary adder, and as it is 4-bit binary adder, then at each input the maximum number that can be given is 4-bit. So in binary that becomes 0 to 9, and whenever we give two numbers, 4-bit numbers, there may be each number can be 0 to 9, and the other number can also be 0 to 9. So the maximum sum, assuming that the input carry is also 1, can be 0 to 19, and the output, the sum of the binary sum of the binary parallel adder can be either of these values. So this would be the binary sum of the 4-bit binary adder. But our final objective is to design a BCD adder. We are not going to design a binary adder. We have already done that, but we are using a 4-bit binary adder, and we want to see how can we make a BCD adder from the 4-bit binary adder. So the sum of 4-bit binary adder can be any of these values in decimal, and in binary they can be like this. The 4 bits are given in these 4 columns, and the output carry is given here. Okay, so this is what the binary 4-bit binary parallel adder gives, and this is what we want to get. The 5 columns. This is what the BCD sum should be, where the 4-bit sum bit are given represented by S1, S2, S4 and S8, and the output carry is represented with C. If we carefully look, the values are similar to the binary sum. The BCD sum is similar to binary sum for the first 10 values. That is, if the sum result of the number is from 0 to 9, then in these cases the binary adder would produce the BCD sum, which are both the same, and for this 10 output combination. But for the rest of values, they are not the same. For these 10 values, the output of binary sum is equal to the output of BCD sum. So in these cases, the binary parallel adder would work as a would work like the BCD adder, but for the rest of cases, the output are different. For these 10 cases, let me give you an example. For example, if the first number is binary number is 3 and the second binary number is 4, then 3 plus 4 becomes 7, so 7 and binary is 0 triple 1 and 7 and the BCD is also 0 triple 1. So luckily for any two numbers for which the sum is equal to 9 or less than 9, then the binary sum and the BCD sum are the same. So for these 10 combinations, the binary parallel adder would produce correct result. But for the rest of combinations, the binary sum is different than the BCD sum. For example, if let's suppose if the input numbers are, let's suppose, 3 and 7, then the output would be 10 and 10 and decimal. 10 and decimal can be represented in binary as 0, 1, 0, 1, 0, but 10 and decimal can be represented as a BCD as 1, 0, 0, where this 0 is represented in 4 and this 1 is 1. So in BCD, 10 represented in BCD is different than in binary, and the same is the case for all other numbers. All possible combinations below this line, the sum of the binary parallel adder, which are shown here, are different than the BCD sum, and in these cases, the binary parallel adder would not function as desired. It would not function according to the BCD sum. So we cannot use binary parallel adder as exactly for all possible combinations. If we are lucky and the sum is from 0 to 9, then it would work correctly for the BCD adder. But if the sum is equal to 10 or above than 10, then the binary sum is different than BCD sum, and we cannot use the binary adder for BCD sum. If we look carefully to these output combinations below this line, then we can see that with every binary sum, if we add 0, 1, 1, 0, that means 6 in the decimal, then it becomes the correct BCD sum. For example, if 0, 1, 1, 0 is added with this binary sum, then it would become 1, 0, 0, 0, 0. Similarly, if 0, 1, 1, 0 is added with this binary sum, then this would become BCD sum, like this. And the same is true for all possible output combinations below this line. So whenever the binary sum of the binary adder is equal to 10 or greater than 10, then if 0, 1, 1, 0 is added, then the output would become BCD sum. So we would call this addition as a correction. This is correction because the binary sum is not equal to BCD sum, so a correction is required to make it BCD sum. Okay, so how to tell this to the binary circuit to do a correction whenever the output of the binary adder is equal to 10 or greater than 10. We need to design a logic circuit for this so that it would trigger the correction whenever the output is greater than 10 or equal to 10. So if we look carefully to the output of the binary adder below this line, then we can see that each time when the carry is 1, then a 6 can be added, and it would make the binary sum equal to the BCD sum. So whenever there is the k, the output carry of the binary adder is 1, then we should need we need to add 0 1 1 0 with the binary sum, the binary sum of the binary parallel adder. And logically we can say that the correction, let's as equal to k when as when this k is equal to 1, we need a correction. Then logically we can write it like this: c is equal to k. But there are some other combinations, these 6 output combinations. We have to also include these 6 combination, and we must be very careful to differentiate these combinations from the above one. So whenever k is equal to 1, there is no k1 in the combination above line. So we need the correction only when the output of the binary adder is equal to 10 or greater than 10. So for these 4 combination, we say that when c is equal to k, when k is 1, logically we can write it like this. And for the other combination, output combination, we can say that when Z8, the output number Z8 is 1 and Z4 is 1. When Z8 is 1 and Z4 is 1, this combination, when Z8 is 1, Z4 is 1, doesn't happen above the line. So this is correct when we say that when Z8 is 1 and Z4 is 1, then also the correction should be added. And logically we can add this to Z8 and Z4. Logically we can write like this. So this addition, this AND term would include these 4 combinations, and we are still missing these 2 combinations, so we have to include these 2 combinations as well in the Boolean equation below. So if we look carefully to those 2 combinations, we see that when Z8 and Z2 are 1, then also the correction should be added, and logically we can write it like this: plus Z8 and Z2. So this is a Boolean equation, and this Boolean equation says that the correction should be added, means 0 1 1 0 constant should be added to the binary sum when either k is 1 or Z8 and Z4 are 1, Z8 and Z4 are 1, or Z8 and Z2 are 1, Z8 and Z2 are 1. And this correction is exactly equal to the column or the output carry of BCD sum C. We can make this column 1 when either of this is true, when either the output of binary adder is 1, or if Z8 and Z4 are 1, or if Z8 and Z2 are 1. So we have defined or calculated the Boolean equation for the correction, and now we can implement this correction with the binary parallel adder to enforce the addition of 0 1 1 0 or the correction. Okay, so to design the final BCD adder, we need a 4-bit binary adder. This 4-bit binary adder would take one 4-bit binary number here, and it would take the other 4-bit binary number here. So as BCD code is also 4-bit, so instead of 4-bit binary number, we can assume that the first 4-bit binary number is the first 4-bit BCD encoded BCD digit, and the other 4-bit binary number is the other BCD digit. So we can give as an input either of the digit 0 to 9 as BCD encoded, and we can also give the second BCD digit here as a 4-bit BCD encoded, and we can provide the input carry here, and the output the sum would be given here, the 4-bit sum, and the output carry would be given here. But this sum would be a BCD sum. If we assume this is a BCD digit 1, this is a BCD digit 2, and we add them and the sum is given here. But this sum, as we see, this is 4-bit binary adder. So the sum would be true or correct only if this sum, the value of the decimal value of this sum is from 0 to 9. But if it is equal to 10 or greater than 10, then this binary sum is not equal to BCD sum. And as we saw in the previous slides, we need correction when the output is equal to 10 or greater than 10. But we have defined or found a Boolean equation that when the value of the equation is 1, then the correction should be added. 0, 1, 1, 0 should be added. To include that correction, we have to implement the Boolean equation here, and when we do that, we get like this. So here is the correction. The C, the Boolean function C is equal to K. This is the output carry of the 4-bit binary adder. So this is K or Z8 and Z4, which is given here, or Z8 and Z2. So this becomes the output carry or C, and this C is 1 when either K is 1 or Z8 or Z4 are 1 or Z8 and Z2 are 1. Then this output carry is 1. So this actually shows the carry C of the BCD sum, and we need correction when this C, the output carry, is 1. Then in that case we need a correction, or we have to add 0, 1, 1, 0 with this binary sum output. So we include another 4-bit binary adder here, and just like this 4-bit binary adder has 4-bit input here and another 4-bit input here. So the output of the first 4-bit binary adder is given as an input to the first binary number of the 4-bit binary adder, and the second number is connected, the middle two input pins are connected with the C, and the first and last pins are connected with 0. So what happens whenever the output of this 4-bit binary adder is equal to 10 or greater than 10, then this logic will create 1, and this 1 would make these two pins as 1, and this pin, these two pins are 0 always, so this would become 0, 1, 1, 0. So a 6, decimal 6 is added with the output. Whenever the binary output of the 4-bit binary adder is greater than 10 or equal to 10, then a 6 is added. Otherwise, this logic will always be 0 and a 0 is added, and that means that the output produced by the first 4-bit binary adder is exactly given here, because 0 addition doesn't affect this output. So this is a BCD adder, while we are reusing two 4-bit binary adder one 4-bit binary adder is used here, the other is used here, and we need 3 logic gates to make the correction. So actually we have implemented this BCD adder with 2 MSI chips. One MSI chip is here, the other MSI chip is here, and if we have this as a small scale integrated circuit, then we reused 2 MSI chips and 1 SSI chip, and we implemented a BCD adder using 2 MSI chips and 1 SSI chip, and the final our output carry, 4-bit binary added output carry. Here it is not shown, but the value of this is always equal to this output carry. So it is not required to show it again because it has already been shown here. So this is a BCD adder. It gets an input carry, one BCD digit here encoded as 4-bit BCD. The other BCD digit is given here, and we have a final output carry of the circuit, and we have a 4-bit BCD sum, and this BCD sum is achieved after the correction. Okay, for further reading and questions, please refer to the book by Maurice Manu, Digital Logic and Computer Design. All the details are given in the book, and also to ask question in the online session, please write a list of questions while you're watching this video lecture. It would be then easy to ask questions during the online session. I hope everything is clear to you. Thank you.